Hi everyone, today we are diving into a crucial topic in computer science time complexities. Understanding this will help you evaluate the efficiency of algorithms and make better decisions when solving problems. Let's explore more common time complexities from the fastest to the slowest with real world examples and practical insights. First, we have WOF1, also known as constant time. This is the fastest time complexity as the runtime doesn't depend on the size of the input. A great example is accessing an element in an array by its index. It's always a single operation regardless of the size of the array. Another example is basic arithmetic, such as adding two numbers. These operations are super efficient and are often what we aim for when optimizing algorithms. Next is O log of n, logarithmic time. This complexity appears in problems where the input size is repeatedly divided. For instance, binary search cuts the search space in half with each step, making it incredibly efficient for large data sets. Balanced binary search trees like AVL trees also have O log of n for operations like insertion or lookup. These algorithms are fast because they reduce the problem size exponentially at every step. Then we have O of n, linear time. Here the runtime scales directly with the size of the input. Think about iterating through an array to find the sum of all the elements. If the array has 10 elements, you'll do 10 operations. If it has 1000 elements, you will do 1000 operations. It's straightforward but still efficient for many tasks, especially when every input element needs to be processed. Now, O log of O, O of n log n. This is where things get interesting. Sorting algorithms like merge sort and quicksort operate at this complexity. They combine linear and logarithmic efficiencies, making them ideal for sorting large data sets. For example, quicksort divides the array into smaller partitions and processes each, resulting in n log n operations on average. It's faster than quadratic sorting algorithms and widely used in real world applications. Next, O of n log k is a variant of linear arithmetic time. This happens when we process n elements while maintaining a data structure of size k, like a heap. A classic example is finding the top k largest numbers in a data set. For each of the n numbers, we perform a O of log k operation, making this approach highly efficient for problems involving prioritization or ranking. Quadratic time, O of n square, is where efficiency starts to drop. Every element interacts with every other element, often resulting in nested loops. For instance, bubble sort compares all pairs of elements in an array. If you double the input size, the runtime quadruples. O of n square algorithms are generally avoided for large data sets but can work for smaller inputs or simple educational purposes. Cubic time, O of n cube, involves three nested loops like naive matrix multiplication. Each element interacts with pairs of elements, leading to a steep increase in runtime. While it's slower than quadratic time, cubic algorithms are still occasionally used in areas like computational geometry or small scale problems. Exponential time, O of 2 to the power of n, is a significant jump in complexity. The runtime doubles with each additional input element. A common example is solving the traveling salesperson problem using brute force. While this approach works for small data sets, it becomes infeasible quickly as the input grows. This is why exponential time algorithms are rarely used in practice without optimization. Finally, O of n factorial. Factorial time represents one of the slowest complexities. This occurs when generating all permutations of n elements. For example, solving problems like the Hamiltonian path using brute force. While fascinating, factorial time is limited to extremely small input sizes as the runtime explodes with even a modest increase in n. To summarize, O of 1 is the fastest and most efficient, while O of n factorial and O of 2 to the power of n are the slowest and rarely practical. By understanding these complexities, you can choose the right algorithm for your problem and design solutions that scale effectively. Thanks for watching, and don't forget to like, subscribe, and share your thoughts in the comments.